We just finished a unit on statistical design, where we learned how to design a study that we can use to obtain data that fairly represents a population. And we learned to be skeptical of statistics presented, as there are many ways to gather data that's biased or data that doesn't represent the full truth. Now that we know how to gather data from a sample, this unit is about statistical inference. And to infer, the key word of inference is to draw conclusions from. So in this unit, we will use data gathered from a sample to infer information about the entire population. Let's consider our first example. A class of students take a math test. Below are their scores. Which group performs better? Well, some students are going to calculate the average, and they're going to say that the average student in class A in this sample of students earned a 73%, and the average student in this sample of students from class B earned an 80%. So the average is higher in class B, so class B did better. While other students are going to say, well, take a look at these scores. In class B, the low scores are way smaller than the low scores in class A, right? In class A, everyone passed except for one student, and that student was just 1 percentage point away from a 70%. So some students are actually going to say, well, class A did better because no one scored as low as some of the students scored in class B. So this turns out to be a pretty subjective question, who did better, but it illuminates some of the criteria we use to compare data sets. The three main criteria we use to compare data sets are the shape of the data, when you graph a dot plot, the center of the data, and the spread. For center, we often use an average to say, like, well, what would be sort of a typical score? Next year in AP Stats, you'll learn about average isn't always the best use of best estimation of typical, but we'll use average for center. For spread, we're going to use standard deviation, more on that later. And for shape, let's talk about dot plots. Suppose you survey students to see how many hours of sleep they get. Display your data on a dot plot below. A dot plot is just a graph where each dot represents a single point of information. And so if we're saying here would be our hours of sleep, only one student is getting 3 hours. You can use an X or a dot or whatever you like to represent that one student who only gets about 3 hours of sleep a night. And there are 2 students who get 4 hours of sleep a night, and 4 students who get 5 hours of sleep a night, and so on. So in creating this dot plot, what you notice is that it's the same thing as a histogram or a bar graph. The only difference is that we're not drawing those physical bars. So if you wanted to draw the bars on top of them, now you've just made this into a bar graph. They're exactly the same thing. What you notice is that the height of each bar gives us an indication for how frequently that occurs. So just by looking at this dot plot, we can see most students get about 6 hours of sleep per night. So that's how we display visually some of the data sets we gather. So assume that these are dot plots in our next example. We said one way we like to compare data is to say, well, what's the shape of the dot plot? This is called a normally distributed dot plot. Because we call it normal because this happens so often. If you gather information about the height of people that are a certain age, right, of males that are adults, or the height of males or females that are 10 years old, or you gather information about blood pressure and all these other things, a lot of data will fall into a pattern like this. We call it normally distributed. So what you'll notice is that it's symmetric. The left and the right look about the same, and it's bell-shaped, right? It looks sort of like an old school bell that you might see in like a church or a dinner bell, right? So we say it's normally distributed if the data is approximately symmetric and bell-shaped. This data is skewed. We would say this is skewed left. You can think about that in a couple of different ways. You would say this is skewed right. I like to say that you name which side has like the trailing off value. So you're naming sort of that tail. This distribution is called bimodal because by 2, mode most popular, right? There are 2 most popular or most frequently occurring values. And this data is called uniformly distributed because every single one of those values is equally popular or equally as frequently occurring. So which are symmetric, which are skewed? Well, this data would be approximately normal because it's approximately symmetric and bell-shaped. This is symmetric, although it's a uniform distribution, aside from these sort of data values sprinkling off to the right. This would be a skewed right distribution because you've got all kinds of data values sort of trickling off. You've got that tail to the right. And this would be bimodal because there are 65 inches and 70 inches are both really popular. Probably the blue and the green are males and females, right? And so this would be like sort of your average male height and your average female height. Okay, approximate the standard deviation. So we've talked about all these different shapes, right? But we've said that the two other ways we like to compare data sets are by looking at the center and the spread. So in a normal distribution like this, it's about bell-shaped. The center, the average will be right in the middle. So our average would be about 50. The standard deviation is a measure of how far your data values are spread apart. Now, standard means typical, and deviate means to go away from. Like if I'm supposed to pick up my little sister after school and I stop by the bodega, I've deviated from a direct path. I've sort of strayed away from a direct path. So to find the standard deviation, you want to see where is my shape concave down. This is like a parabola that's pointing down. Where's my shape concave up? You've got sort of two halves over here, and in between is almost like a straight line. Do you see that? And so you want to sort of slice that straight line piece in half, and then standard deviation would be your distance from the mean to this point. It's called the inflection point, the point where the concavity changes, right? It's concave down right here and concave up right here. And so inflection point is that point where concavity changes. So my standard deviation is about 10 in this case. Okay, one more example for today. A local utility company wants to gather data on air conditioners. Okay, so they're asking people, do you have an air conditioner? How old is it? Here's the distribution. So this, guys, is just a histogram or a bar graph or a dot plot with all those bars drawn on top of the dots, right? So we can tell most people have an air conditioner that's about 21 years old or so. A, would you describe this as approximately symmetric or skewed? Real life data is not often going to look perfect, although the more data you gather, the more closely we can resemble this shape. Since you can fit a bell-shaped curve on top of it, and it's about symmetric, we'll say it's approximately normally distributed, right? It's approximately symmetric. It's not perfectly symmetric, but more or less. Notice that when I fit the curve, I'm leaving some gaps under, and I'm also cutting some values off. You want the values of the gaps and those that you cut off to be approximately the same. So you're not fitting a curve like this, where it's just sitting on top. This isn't like tin foil on your leftover lunch where you can't like really cut any off. No, feel free to smush some of the frosting if you're using tin foil on a cake, right? So you're sort of smushing it down. You should be cutting off some values. Okay, is the mean closer to 15, 20, or 25? Well, we sort of drew it in. I would say the average is about 20. Because that's the center of my symmetric curve. And how about the standard deviation? Well, I see that this shape is concave down about here and concave up about here. So my inflection point is approximately here. And so my standard deviation would be the distance from the mean 20 to that inflection point at 23. So my standard deviation is about 3. Let's double check it on the other side. Concave up maybe here. Do you see that sort of straight edge in the middle? So maybe the middle would be here. This is about at 16, so my standard deviation would be maybe 3.5, somewhere between 3 and 4.